Welcome to our presentation. I am Fernando Trejos Suarez, and these are my collaborators, John Haviland and Elena Kim. And so we will be talking about constructions of generalized more sums than difference sets in higher dimensions. So for some background on the MSTD set problem, if A is a finite set with integer coordinates in d dimensions, and we denote its size in the usual way, we can define the sum set and the difference set, which are defined in a pretty natural way. The sum set is all the stuff that we can write as the sum of two elements in A, and the difference set is all the stuff that we can write as the difference of two elements in A. And so we say the set is difference dominated if the difference set is larger, balanced if they're the same size, and then sum dominated or MSTD, more sums than difference, if the sum set is larger. So some motivation, there's lots of classical problems in number theory that care about the sum set or the difference set of A. So for example, the Goldbeck's conjecture can be restated as saying that the set of even numbers is contained in the sum set of the set of prime numbers. And Fermat's theorem can be restated as a statement of the intersection of the sum set of the set of nth powers of integers with itself. So a natural question is, what are the sizes of sum sets and difference sets? So how big do we expect the sum set to be? How big do we expect the difference set to be? So generally the difference set will be larger. And this just comes down to the general heuristic that addition is commutative while subtraction is not. You can get one thing by summing together x and y, but you can get two different things, x minus y and y minus x, by taking their difference. So in general, the difference set should probably contain more elements, as each pair is more likely to give us something new. This doesn't, of course, that is not accounting for overlap, but it's just a general heuristic to say that the most sets should be difference dominated. So this is the smallest example of a more sums and difference set. And even for this small example, clearly it's relatively large. It's quite a non-trivial example, and the sum set and the difference set are only differ by one. So these sets are kind of very carefully chosen. And Nathanson, one of the first people to study this problem in depth, estimated that with the right way of counting, the vast majority of sets should be difference dominated. So what he means here is that generally, as the size of the sets increase, we should get that approximately a vanishingly small percentage should be sum dominated. But this was actually contradicted when Martin and O'Brien, two of the current experts in the field, said that prove that a positive percentage of sets are MSTD as n tends to infinity. And Zhao showed a particular bound for this. In particular, he showed that the limit of the percentage is strictly larger than around 4.3 times 10 to the negative fourth.
The next thing we're going to talk about is a generalization of the notion of MSTD sets. So first we want to look at how we can construct normal MSTD sets. If we're looking at this, we know an element is in the sum set if we can find two elements of A that sum to X. An element X is in the sum set if we can find two elements of A which sum to X. If X is in the middle of the interval 0 to 2n, which is the interval of all possible elements of the sum set, then there are going to be lots of pairs that can sum to X. For example, for n, which is exactly in the middle, there are about n over 2 pairs that can do this. On the other hand, if X is near 0 or 2n, then there are very few pairs. So if X is near 0, then both elements of the pair have to be near 0. And if X is near 2n, then both elements of the pair have to be near n. So this means that with high probability, the middle of the set is going to be full. On the other hand, the fringes, which are the areas near 0 and 2n, these are going to be where we get missing elements. And these are what we want to control if we want to find sets where the sum set is larger than the difference set. We want to control how many elements are missing from the sum set and the difference set by controlling what the fringes are in the original set. So to go a little bit further, we're going to generalize the notion of sum sets and difference sets. So given a pair S and D, we're going to say that SA minus DA is A added to itself S times and then subtracted D times. So an element of this set would look like A1 plus a bunch of A's through AS, and then subtracting A sub S plus 1 through A sub S plus D. So this is what these elements look like. We're adding a bunch of elements and then subtracting. These were studied by previous years of the small REU, and these students showed that given any two pairs, S1, D1 and S2, D2, where S1 plus D1 is the same as S2 plus D2, there exists a set A so that S1A D1 minus D1A has more elements than S2A minus D2A. They also showed that given any k, any natural number k, there exists a set A so that as long as C is less than or equal to k, CA plus CA is going to have more elements than CA minus CA. And finally, they showed that even though these examples exist individually for each k, there's no set A which is an example for all k. So these examples only work in specific cases. So our question is, how can we send these results to higher dimensions, and if so, how? So for example, given any two pairs, S1 D1 and S2 D2 like before, can we find a two-dimensional set so that S1A minus D1A has more elements than S2A minus D2A? We can do this using some constructions that are inspired by the one-dimensional constructions. So similarly, given any natural number k, can we find a two-dimensional set A so that CA plus CA has more elements than CA minus CA whenever C is less than or equal to k? And again, we can do this, again, inspired by the one-dimensional arguments. So finally, we would ask a corresponding question to the last one for one dimensions, which is there an example of a set A which works for all k? So in other words, does any example of the sets for the second question work for every value? And we've been able to prove this given some restrictions on the possible sets, but we haven't gotten the fully general case. So we can do this in some cases. So before we look at these two-dimensional constructions, we want to look at some one-dimensional constructions first. And specifically, how did previous small students construct these one-dimensional generalized MSTD sets? So the important thing here, remember, is that we're looking at the fringes, and the middle is not very important. So what we're going to do is define these left and right fringes here. And what's happening here is that we're taking an interval from 0 to 2k plus 1, and we're deleting one element at the beginning and k minus 1 elements towards the end. Then to get the right fringe, we're going to do a very similar thing, but we just use one more element at the beginning. So we kind of shift all the deletions over one. Then we take a full middle in the set, and we put the left and right fringes there, and we kind of reflect the right fringe over. So this gives us the structure here where the blue elements are the fringes on either side, and the red elements in the middle are what we call the middle of the set, and that's completely full where it's shown. So we can see we've got this nice structure, and these fringes are great because they maintain their shape when they're added and subtracted. So this means that when we're doing these generalized sum sets, they're going to maintain their structure while we're doing iterations of adding the set to itself and subtracting it. However, after enough additions and subtractions, the middle is going to kind of expand out because that's what happens when you do these additions, is the middle expands and eventually it will cover over the holes in the fringes. So even though the fringes are maintaining their structure, the middle gets so large that it just takes over the entire set. So then the question is, how can we generalize this? How can we take this to two dimensions? And we're going to do a very similar construction here. We're going to have middle and fringes. So the middle this time is going to look like a cross here, which is completely filled in. Then we'll have some space and then fringe sets, which are kind of inspired by the one-dimensional fringe sets. So again, we've got this middle structure here, which now looks like a cross. But then to see the delicate structure in the fringes, we need to zoom in a little bit. So looking at the bottom left corner, this is what it looks like here. So we've got, it's almost completely filled in, but if we look at the left and bottom edges, we can see we've got the exact same structure as the one-dimensional fringes. So we've got one element deleted towards the start, and then a bunch more elements deleted towards the end.
Now that we've constructed these sets that John just showed, we can then prove that for S1 plus D1 equals S2 plus D2 all equals to K, that we have a set such that the cardinality of S1A minus D1A is greater than the cardinality of S2A minus D2A. We can then prove using the same construction that if we have a x1 plus y1 equals x2 plus y2 specifically not equal to K, then the cardinalities of these two sets will be the same. Then using these two facts, we can use these sets to construct another set, A prime, two-dimensional, such that the cardinality of CA prime plus CA prime is greater than the cardinality of CA prime minus CA prime for C between 0 and K, or between 1 and K. We're going to call these sets K-generational. In order to construct this A prime, we're going to need to introduce the concept of base expansion. So what is base expansion? It's basically a way to combine two sets to give it the nice properties that we want. So for two-dimensional sets and a sufficiently large scalar M, we're going to define a third set C as the scalar times the set A plus the set B. And the most important thing about base expansion is that we have the cardinality of SC minus DC is equal to the cardinality of SA minus DA times the cardinality of SB minus DB. So let's just quickly recall the definition of a K-generational set. So then to construct a set that's K-generational, we're going to need to strategically pick AIs for I between 1 and K. So for each I, we're going to choose AI such that the cardinality of IAI plus IAI is greater than the cardinality of IAI minus IAI. And then for J not equal to K, we're going to have the cardinalities are the same. Then we're going to use base expansion to use these AIs to define a set A. And then with this set A, we're then going to prove that this set is actually K-generational. So first we're going to look at JA plus JA, and just somehow as defined in base expansion, we know that we can write its cardinality as this product here. Then next we're going to split up product into two parts. Now we're going to look at the right hand of this product, right-hand side of this product. So we can replace JAI plus JAI with JAI minus JAI just because of the properties of the specific sets that we chose. And then we're going to look at the left-hand side of this product, and we're also going to replace JAJ plus JAJ with JAJ minus JAJ and put in an inequality sign there. And again, that's because of the properties of the sets we chose. And then finally, again, because of how the set was chosen through base expansion, we can combine it all into this one product here. And then we have the set as K-generational. Here we can note that we have actually proved a much more generalized version of this, where the coefficients are much more generalized. However, the proof for that, although it's very similar to this, is notationally much more difficult. So for this presentation, we're just showing K-generational sets. Now a reasonable question to ask after this is if there are any two-dimensional sets such that the cardinality of Ka plus Ka is greater than the cardinality of Ka minus Ka for all K in the natural numbers. So recall in the one-dimensional case, the answer was no. But to examine this in two dimensions, first we have to describe the behavior of Ka. So in one dimensions, we have this theorem by Nathanson. Basically, we have a one-dimensional set A. It's ordered from least to most. It has GCD 1. And then if you look at the last line of this theorem, for sufficiently large K, we have Ka is the union of a set on the left side of the set, a set on the right side of the set, and then a completely filled in middle. So what this will mean is that for a large enough Ka, this set will always be missing a constant amount of points, even though the interval that it is in will grow as K grows. In two dimensions, we can have a similar theorem. However, there are some differences. Those are highlighted in red. So the first difference is that our set can't just be any set. It has to have some specific points in the set, which are outlined in the theorem. And then Ka, instead of missing a certain amount of points, the points missing from the set are going to grow linearly. So a quick outline of this proof. We do have a rigorous proof, but for this presentation, we're going to do a nice proof by picture. So for A with the characteristics that we outlined before, and for sufficiently large K, the set Ka is going to look something like what we have in this picture. So you'll note that there's a completely filled in middle, and then there's missing rows and columns along the edges. So because of these missing rows and columns, that will cause the amount of points missing from Ka to grow linearly with K. Then we can use the previous theorem to prove this one, which states in the end that the cardinality of Ka minus Ka is greater than or equal to the cardinality of Ka plus Ka for sufficiently large K and for the specific sets A with the properties we want. So again, we're going to use a picture to kind of explain the proof. So first note that Ka minus Ka and Ka plus Ka are both going to be subsets of rectangles of the same size. So to compare the size of these two sets, we want to look at the amount of points missing. So for Ka plus Ka, when we add it to itself, the center is going to be preserved as well as the rows and columns. There are not going to be any additional points. But when subtracting Ka from itself, it's also going to preserve the center and the rows and columns on the edges. However, points in the rows, columns, and middle can interact with each other to possibly create additional elements in this set. So it may have more elements, or it at least has the same amount of elements.
So the last thing we're going to talk about is some other constructions, specifically going to higher dimensions and modifying the constructions that we've already made in a couple ways. So the first thing we're going to look at is higher dimensional constructions. And specifically, what would the middle and the fringes look like in D dimensions rather than 2? Of course, we can't really visualize anything higher than 3 dimensions, so we'll just go to 3 dimensions and imagine it for higher than that. So in 3 dimensions and higher, the cross shape that we have in the middle for 2 dimensions is going to transfer up to something very similar. You can see here, it's just this kind of 3-dimensional cross shape where we start with the cube and then remove the corners of it to give some room for the fringes, which are going to be D-dimensional boxes. So in any case, for higher dimensions, the construction will be very similar to this, where we take a box and remove the corners to get the middle of the set, and we leave that completely filled in. So on the other hand, the fringes are going to be boxes. They're going to be small enough to fit inside the parts that we removed from the box initially to get the middle. And then what we're going to do is take 3 of the edges and place the 1-dimensional fringes on them so that they meet at a corner, which is kind of shown here with this 3-dimensional cube, where you can see that we have the same fringe structure along 3 of the edges that meet at a common vertex. And then similar to the 2-dimensional case, for each corner, we're just going to rotate this fringe so that the 1-dimensional fringes face out from the center. So these are always going to be the 3 outermost edges in some sense. And this is how, and then again, as before, these structures, these fringes preserve their structure under addition and subtraction, but with enough iterations, the middle fills up the set completely. And so we get the same niceness for finding generalized MSTD sets in D dimensions rather than just 2 dimensions.
So all the previous constructions that we've done have been subsets of squares and cubes and higher dimensional cubes. But this begs the question of whether we can put our sets as subsets of other shapes. So from previous work of MSTD sets in higher dimensions, we know that in order for the sum set and the different sets to have nice properties and nice behavior, they should be subsets of a shape with integer vertices and is locally point symmetric. So the only shape that falls into this category are parallelograms. So we're going to look at parallelograms first in 2 dimensions with slope m. So slope m means that we originally had a square and then we took the sides that were parallel to the y-axis and sheared them with slope m. So then we can quickly define a map that will shear our sets. And then applying that map to one of our sets, we're going to end up with things that look like this. In higher dimensions, we can note that we're going to have d times d minus 1 over 2 positive directions to shear the set in. So then we have to define that many slopes. So for this, the notation is mij will be the slope of the jth axis that is sheared in the ith direction. So then using all these slopes, we can define another map that will again shear our sets and turn them from cubes into parallelograms.
To conclude, so we've shown that the elements missing from Ka grows linearly for certain A in order to help control the size of the sum sets and the difference sets. So in the future, we want to show that the elements missing from Ka grow linearly for all A, which is namely pretty much exactly what we would need in order to generalize our results on the K generational sets to every possible case in 2 dimensions or higher dimensions. And then, well, so going back to the more general question about d-dimensional MSTD sets, you know, previous work in 1 dimensions has shown positive percentages for MSTD sets, chains of generalized MSTD sets, and K generational sets. So in the future, we would hope to show a positive percentage of all these quantities for d-dimensional sets. So any results in higher dimensions, 2 or higher. And this is something that we haven't really covered in our presentation, but something that we really hope to look into for a full generalization of the original problem. And so, yeah, so we will now be taking any questions, and thank you for our mentor, Professor Stephen J. Miller, Williams College, Yale University, and the NSF for their generous funding, and of course, the coordinators of the Young Mathematicians Conference.